This week, we will focus on internal flow. This is chapter 8 in your textbook. So internal flow is actually more common than external flow. And as you can imagine, there are many heat transfer processes that involves internal flow. Most of the heat exchangers involve a flow inside a tube. And there are shell and tube type of heat exchangers that involves internal flow. And as you can imagine, there will be various situations the internal flow is experienced in the context of heat transfer. So our goal in this chapter is try to understand how to estimate the convective heat transfer coefficient for internal flow. So first, as we mentioned earlier, in general, you must always consider the hydrodynamics and heat transfer together. So in general, the flow behavior strongly influences the heat transfer behavior. So let's just remind ourselves about the hydrodynamic layers and hydrodynamic boundary layer. We briefly talk about this in chapter 7, but I want you to think about this in the context of internal flow. So let's just start to remind ourselves about the development of boundary layer. So when you have an external flow, if you have a flat plate, the flow is gradually because there is no slip boundary condition, there is a friction here. So this effect gradually builds up, and you'll have initially laminar flow, and this gradual continuation of these effects will lead to transition and then turbulent boundary layer. So now the question is, what happens if you have an internal flow? So just think about, you have this situation. Instead of one plate, we have two plates. Let's say we have two parallel plates, and as you can imagine, there is a boundary layer developing from each side. So that means eventually these two boundary layers will merge. Okay? So that means one difference between internal flow and external flow, there will be basically the boundary layers from two sides. Even if you have a cylinder, the same thing will happen. So you'll have an entry region. So we call this region as hydrodynamic entry region, where two boundary layers meet. It's called entry region. Okay? So after these two layers are merged, then you have fully developed region. So now the first question is, how do we estimate this length? What is the hydrodynamic entry length? The second question is the heat transfer behavior is different in hydrodynamic entry region than fully developed region? That's the second question. So for a circular pipe, so the criteria for transition from laminar to turbulent is Reynolds number, and when the Reynolds number is greater than, when it's less than 2300, we have a laminar flow. When it is between 2300 and 10,000, we have transitional flow. When the Reynolds number is greater than 10,000, we have turbulent flow. Okay? So now, what is the hydrodynamic entry length? What is the length, this length? So if you have a laminar flow, the entry length, hydrodynamic entry length to reach the fully developed flow is Reynolds number for this particular diameter multiplied by 0.05 multiplied by diameter. And this is going to give us the length. And as you can imagine, if you have a larger diameter, it will take more distance for these two boundary layers to merge. So it is going to be greater distance until you reach the fully developed region. And if you have a turbulent flow, so in general, this distance is more or less constant. It is somewhere between 10 to 60. Okay, so it's not very accurate. You just have a range in here. So if you want to just take the medium value, let's say 35. So you can do 35 times d turbulent. So that is basically going to give you roughly the distance for enter region if you have a laminar flow to start with. So in this analysis, we are going to approximate in general, when you have a flow inside a cylinder or between two parallel plates, you have a parabolic velocity profile. So it has a maximum in the middle, it has minimum at the walls. Because walls have no slip boundary condition, fluid molecules stick to the wall, so they don't move, but the velocity is maximum away from the wall, so that's why you usually have this parabolic velocity profile. But the analysis with this kind of variable, this is, let's say if this is r, radius, velocity varying with radius, it's going to be very complicated analysis. So we tend to approximate this velocity profile with an average. So we average it across this cross-sectional area and divided by the cross-sectional area. This gives us the mean velocity. This is the idealized situation. This is how we are going to assume the flow is behaving when we are driving the convective heat transfer coefficient for internal flow. So again, this is a reminder from fluids. So if there's a pressure gradient here, delta P by delta X, if this pressure gradient is driving force for the flow, so the velocity profile will be minus 1 over 4 mu times pressure gradient. This is usually a constant. And R0 is, R0 is our radius. R is the position, any position R here. So this is telling us how the velocity is changing with R. And this shape is a parabola. And if you want to get the mean value, so you integrate it across the cross-sectional area. So, and then divided by the cross-sectional area. This is, so if the cross-sectional area is pi r squared, this is AC. 2 pi r, dr is the dAc. So if I replace this here, replace that here, so you can actually calculate, you can obtain the average velocity. And if you do this math, so you'll be getting a mean velocity, which is basically the pressure gradient multiplied by radius squared over 8 mu. And if you take the ratio of the actual velocity at any position r and mean velocity, you get this relationship. Okay. So now, if you want to, in general, whenever there is a fluid flow, if you have a finite viscosity, the pressure will drop because there is frictional losses on the walls. So that means as the fluid moves from one side to another side, it is going to lose energy. There's going to be a pressure drop. And the way to estimate the pressure drop is using the friction factor F. So this F is the friction factor. We have in chemical engineering, we mostly use the Fanning friction factor, but also sometimes we use the Moody friction factor. So the difference between them is only a factor of 4, okay? So basically in here I'm giving everything in terms of Moody friction factor, okay? Moody friction factor. So if you want to calculate the Moody friction factor for a laminar flow, it is 64 over Reynolds number. And what is why do we need, what can we do with this quantity? So let's say you are designing a heat exchanger and there is a very long pipe inside it. So there you first calculate the pressure drop and then you know the volumetric flow rate of that system. And from the product of these two, the volumetric flow rate multiplied by the pressure drop gives you the pump power, okay? So it is important you should able to decide or design what kind of pump you need to be able to handle a heat transfer process. So the equation that I showed you, this is for laminar flow. And we have Moody diagrams that are more comprehensive, that tells us the friction factor as a function of Reynolds number. So this graph is fairly easy to read. So basically, first you calculate your Reynolds number for the system. And then you determine the roughness ratio. Let's say if you have a pipe. So if you zoom in at the molecular level, you see a roughness here. This roughness called epsilon. So epsilon over d is the roughness ratio, and you calculate the roughness ratio if you have a smooth pipe versus slightly rough pipe. So you find out what is your roughness ratio. You have Reynolds number, you have the roughness ratio, and then you read your friction factor. Okay? So that is the idea behind this. And after you have the friction factor, so you basically, if you want to calculate the pressure drop, the pressure drop is friction factor multiplied by rho u squared over 2 times diameter times length. Okay? Okay, so if you want to calculate dp over L, so instead of dp over dx, if you want to calculate the pressure drop across a certain length, so you just calculate fanning friction factor multiplied by rho velocity squared over 2 multiplied by d, multiplied by length divided by d.